Okay, just some questions about the funniness of integration. So the weirdness becomes, when you take a derivative of a function, so you put some function in here like cosine of x, what you get out is another function, right? So you just get out, what in this case, the derivative of cosine is negative sine x. Okay. For integrals, though, it's not like that. It's really not put in one thing, get out one thing. For integrals, you're putting in one thing and you're getting out a family of things. So for the integral version of this, if you integrated something like negative sine x dx, I'm not just going to get cosine out. I get cosine x plus a constant. And what that means graphically is that you have not just cosine, right? It's not just cosine, but it's every shifted version of cosine. So remember, if you have a function f of x, y equals f of x, and then you add something to the outside of it, what does that do? It moves it up, right? So if you had y equals x squared, that would be this, y equals x squared. If you have y equals x squared plus 1, what does that do? Well, that just takes this graph and shifts it up 1, right? So what is the cosine of x plus c? Well, that's going to be, and it goes on, the cosine graphs go on forever. That's going to be just all these different cosine graphs shifted up and down forever and ever and ever. Okay, that's what this represents. Okay, it doesn't represent one particular guy, like this guy here. It represents a family of guys. Okay, and this constant c is basically kind of a way of populating all of these. So you could start with c equals 1 here, and then you would have to move up to here. So basically what I'm saying is that if I had cosine of x plus 1 plus c, that's equivalent to this thing right here. Okay, this just means that the sort of generator graph is right here as opposed to right here. Okay, but in either case, the generator of the big picture has the same shape. It's just positioned in a different place. Okay. Okay. So, anyways, the issue then comes to bear in problems like number 41. Okay. So clearly, we have the integral of sine of 2x cosine 2x dx. And there's like 3 different ways you can do this problem. Okay, and they're all the same. All the answers are equivalent, believe it or not. And so first is the trig method, doing a trigonometric identity. And I don't remember my trig identities that well because I never teach trig, but it's probably like a half angle formula or something like, what is it, sine of 2 theta equals 2 sine theta cosine theta, something like that. You have to use this identity, sine of 2 theta equals sine of 2 sine theta cosine theta. I bet it was that identity. All right, let me look. It's probably in Calc Chat or something. Sure, yeah, so if you want to rewrite this thing, how do you do that? Well, you could replace these with 2's. So I have 2 sine 2 theta cosine 2 theta, and then over here that'll be sine of 4 theta. And then to replace this thing, you have to divide both sides by 2, right? So sine of 2 theta will equal sine of 2 theta cosine 2 theta will equal 1/2 sine of 4 theta, right? So that's probably the first way they show on Calc Chat. Okay, let's just use a trig identity and rewrite this as 1/2 sine 4 theta d theta, and then we could do a u sub on 4 theta. So du will be 4 d theta, and then d theta is du over 4. Right? So rewriting this thing, you'll get 1/2 integral sine u times d theta, which is now du over 4, and then you get 1/8 integral of sine of u is just negative cosine u, okay, plus c, and then back substitute negative 1/8 cosine of 4 theta plus c, right? Okay, so let's see what CalcChat sort of did there. My stupid screen won't scroll up. I hate this freaking. Please. For some reason I can't get the stupid thing to scroll up at all. Like, I have so many stupid bars, like scrolling bars. I get the tweets to. Oh, I can move it around like that. Really? Frick! I'm just gonna have to reset the thing. What problem is this? I don't even know what problem this is. Oh, there it is. Oh, that was the last answer they got. Okay. All right. So, what are some other answers then? And you know, where's the confusion? And it all goes back to this issue right here. Basically, any constant you have out here, you can just allow it to be absorbed by this value here, and then ultimately. This thing is kind of like the generator for all of these curves in this family. And it doesn't really matter which curve you want to think of as the generator. You can think of it as cosine of x plus 1 is here, or you can think of it as cosine x. Okay? It's that idea that's going to be the reason why we can have 3 different answers. And any answer you pick is fine. I am smart enough to figure it out, and I'm not going to mark you wrong, okay? Okay, so anyways, let's look at a different way to do it then. So let's try sine 2x cosine 2x dx. So a different way to do it would just be a u sub for either cosine or sine, right? So let's say u equals sine 2x, and then du will equal cosine 2x times the derivative of 2x, which is 2, dx, and then dx is du all over 2 cosine of 2x, right? So I do my substitution here, and I'll get the integral of u times cosine of 2x times dx, which is du all over 2 cosine of 2x, right? And then the cosine 2x divide out. I'm left with a 1/2 in front. Integral of u du. Sorry, I'm going off the page. And then that will be 1/2 u squared all over 2 plus c. Back subbing, I get 1/4. And then u now is sine squared 2x plus c. Okay. Right. So how is this thing related to this thing? And it's not exactly the same, but they differ by probably a constant. Okay. So we're going to have to go into the world of trig. And I need to get my trig book ready so I can remember my identities. Okay. Okay, so here we got some trig identities for me. Right, so how do I get from 1/4 sine squared 2x plus c to negative 1/8 cosine of 4 theta plus c? This is the question. All right. How are those two guys equivalent? Okay. So first off, I can probably do a nice half-angle formula on this guy. And so note sine squared of 2x is equal to 1 minus cosine of 4x all over 2 plus c. Right? So this thing then becomes, if I do a replacement for this with this, it's just going to be 1/4 times 1 minus cosine of 4x all over 2 plus c, right? And then you can go, all right, well, that's the same as 1 minus cosine of 4x all over 8 plus c. And then you're kind of saying, all right, well, that kind of connects, right? But not quite. It's off by a constant. And that's where my first beginning part of the lecture comes in. Cosine of 4x all over 8 plus c. And on the other side, we have this thing, right? This thing right here. Let me rewrite it so you can see it. The other answer was negative 1/8 cosine of 4 theta plus, and of course now you can't see it. The other answer was negative 1/8 cosine of 4 theta plus c. Right? I should be using an x or whatever the variable was. But the point is, look, this thing right here just shifts up the generating curve, if you think of it that way, as a little higher in the plane, right? So you know, this thing, whatever, you know, off the top of my head, it's probably looking something like this, you know, and then that will generate all these other curves when you add in the plus c. Okay, so plus whatever, you're going to get that family. If you use this guy instead, you'll end up with the same idea. It's just this is shifted a little bit higher, and that's the generator. Okay, so maybe it's sitting right here instead. But when you add in the plus c for any c, and you're allowed to use any c you want, you basically end up with the same picture as you would get if you use this other guy as the generator. This thing as your generator, or this thing as your generator. They're the same thing. It's just one is shifted up a little higher, but when you add in the plus c to get your family, you end up with the same family. Okay. Okay. There is one more answer then, which is probably a little easier to get at, right? So 1/4 sine squared 2x plus c is more closely related to this other one. So what was the other way to do this integral? So I have an integral of sine 2x cosine 2x dx. And this time just do a u sub on cosine. So u is cosine of 2x. du is negative sine 2x dx. And so dx is negative du all over sine 2x. Okay. All right, so doing our substitutions, I end up with the integral of sine 2x times u times negative du all over sine 2x. The sine 2x's divide out, and you're left with a negative integral of u du. Oh, I forgot a 2, so there has to be a 2 in here by the chain rule. So over 2, and then this would be negative 1/2, so there'd be a 2 down here. So this would be negative u squared over 4 plus c, and then when you back sub, you get negative cosine squared 2x all over 4 plus c. Right? And you're wondering, how is that answer the same as that answer? And again, it's the matter of the generator is all that's really important. It doesn't matter where it's positioned. When you add in the plus c, if it's positioned here, you're going to get all the other ones. If you add in plus c and it's positioned here, you end up getting all the other ones. So it's idea of a basis maybe is kind of the idea. If you took like linear algebra, you talk about bases, the thing that generates the entire space. Okay, so it's like I don't know, maybe think of it in terms of viruses. That one virus, you know, it doesn't matter if it's in your lungs or if it's in your brain. It's going to start multiplying, and you end up with the same illness. You know, it's that idea. So, anyways, yeah, let's go ahead and figure it out. So negative cosine squared. We can use a Pythagorean identity on that. So that would be 1 minus sine squared 2x. All over 4 plus c, and then you would have, if you butterflied it, negative 1/4 plus sine squared 2x all over 4 plus c, and so the generating curve right here is this thing, and the generating curve for that other answer was this thing. Okay, so again, the generator for this, I'm not sure what it looks like. It probably looks something like, I don't know, like this maybe. Sorry. So maybe that's up there, and then when you add in the plus c, you get the family, right? But what I'm saying is that this guy will be positioned somewhere else in the plane. So maybe, I forget where I put the first one over. Maybe it was right here. This guy is probably positioned lower, right, because of that minus 1/4. So maybe it's this one here. Okay? But the point is, when you add in the plus c, what you get is the whole family. So these answers are not one individual function. It's a family of functions, and to populate the plane with those functions, it's a matter of adding in this plus c. So these constants don't really matter. And as a matter of fact, in general, what the book likes to do and what math people like to do is just take this constant and stuff it in here. This is like a black hole of constants. And you'll worry about this significantly more once you get the differential equations, okay? So it may not be important here, but it will be important there. Okay, so hopefully that helps you a little bit. I'm sorry if I'm blowing through it. I am on a lot of coffee this morning, okay? All right, so anyways, that's the spiel about 41. Then 43, let's take a look at that guy. Maybe this is some sort of trig issue, I'm not sure. So cosecant squared x all over cotan cubed x dx. Okay, so what I like to do with these is just rewrite everything in terms of sines and cosines and hope stuff works out for the best. But if you do see like a derivative of the function in here, you can do that as well. You can simplify that way. So, all right, so the derivative of cotan, sure, is cosecant squared. So let u equal cotan of x, and then du will equal negative cosecant squared x dx, and then dx is equal to negative du all over cosecant squared x. Okay. Okay, so do your substitutions. We have cosecant squared x over u cubed times negative du all over cosecant squared x. And then this would just be negative integral of u to the negative 3 du. And then that's equal to negative u now to the negative 2 divided by negative 2 plus c. And then you can rewrite that as 1 all over 2u squared, but back subbing, you get a cotan x squared plus c. And who knows what they did, right? They probably did some weird identity. Let me look at their answer. Okay. So let's see what they got. This is 43, I think they said. And of course, it's not letting me scroll down. Thank you for being a piece of junk. Okay, so there's some simplifications. I mean, this answer is fine, honestly. It would depend on where you're working or what you're doing. Like if you have to put your answer into a computer, maybe this would be annoying to type in, so you want a nicer answer. You could use Pythagorean identities on this guy, and that's what it looks like the book did. So you could rewrite this as 1 all over 2 secant squared minus 1. Right, secant squared x minus 1 is the same as cotan x. And then what did they do there? Okay, so they rewrite oh, I see what they did. Okay, so they rewrote this first off as 1/2. 1 over cotan is the same as tan. So you get tan squared x plus c. And then this is equal to 1/2 times the secant squared x minus 1 by the Pythagorean identities. And then you could distribute the 1/2. Okay, so then that would equal 1/2 secant squared x minus 1/2 plus c. And these constants, again, it's the generator idea. This thing as your generator is equivalent to just having 1/2 secant squared x as your generator. Okay, so you can drop this business and just replace it with this. Okay? And the way you'll start to think of it when you get the differential and stuff like that, this constant is absorbing, this big constant here will absorb the other constants. In general, if you need to know kind of which curve you're on, it'll be determined by initial values. So you'll be given some point in the plane, and given that point, you could solve for c. So you'll be given a point x and y. Okay, so this answer right here is y equals 1/2 secant squared x minus 1/2 and plus c, right? And if you know x and you know y, you can solve for c, regardless of what this thing is. It'll just kind of shift itself to make it the particular curve that you want. Okay, so it's a lot to absorb, really, but you'll get used to it. Okay. All right. So what else did we have issues with? Number 71. Okay, so let me take a look at that. I got to go in my book to find it, and my book's online because I left all my books in my office. 71. Where are you? 71? Another trig guy. So we have cosine cubed 2x sine 2x dx. Okay, so this looks like the derivative of cosine. So that's what I'll do for my u sub. U is equal to cosine of 2x, and then du will be negative sine 2x times 2 dx. That's my differential, and then dx will equal a negative du over 2 sine 2x. Okay. And then I could substitute that material in for whatever I need. So I'll have u cubed times sine 2x times dx, which is now negative du all over 2 sine 2x. Okay, and then you can cancel these guys out. You'll get negative 1/2 integral of u cubed du. Okay, and then that's equal to negative 1/2 u to the 4 over 4 plus c. And then you back substitute, so you get negative 1/8 times cosine of 2x to the 4th plus c. Okay, let's see what the book did. That's what the book did. Okay, well, there's that. Oh, they did like a double U sub or something? Okay. There's more than one way to skin the cat. I don't know why the Larson book has decided to start doing these U subs in this weird kind of way. I think it's so you can do them easier in your head. But the truth is, if you're programming a computer or something, this is the way you would do it. Other teachers do it differently, but you could do it my way or you could do the book's way. I think my way's better. And I'm sure every teacher that teaches this will tell you their way is the best way. But you can do it any way you want. Ultimately, it's up to you. Okay. Let's look at 79 and see what that is. It's some weird. Okay, so the integral from 1 to 9 of 1 all over square root of x times 1 plus square root of x squared dx. And let me read your letter there, Ben. See what the heck you had an issue with. 71, I'm not sure how to get the required answer. Hopefully that was, you got the answer now. There for 71. 79, you said the book has, the answer is 1/2, but my answer was 2 ln 4 minus 2 ln 2. Okay, so 2 ln 4 minus 2 ln 2. Maybe the same thing. So, no, I don't think it is the same thing. The answer I got was 2 ln 4 minus 2 ln 2. And I verified it using a different site. Okay, so number 79. Okay, I'll go through it. And maybe it's equivalent. It doesn't look like it is. This would be 4 ln 2 minus 2 ln 2 is just, yeah. And you're saying, it's saying the answer is 1/2? Let me look. Yeah, the book says it's 1/2. Calc Chat says (1/2) as well. Okay, I have no idea why you're getting natural logs in there. There should be no reason for it. Maybe it's the wrong question. There should be no natural logs in your answer. And I don't have no idea how a computer, I assume you use some sort of computer algebra system to figure it out. Okay, so I don't know, maybe there's another way of doing substitution on this. Maybe u is square root x instead, and maybe that would take care of it. And then I have no idea. So du would be end up being, I have no idea. There's no way that it could equal two different things though. So you would have to, I didn't get the attachments in the thing you sent there, Ben, so I don't know what you're talking about, but I mean, I could go through the problem, but I know I'm going to get what they got. I'm going to get 1/2 as well in the way I do it. Okay, so you got to be careful going to different sites. The algorithms that are embedded in those different sites, sometimes they're coded in a way that a computer can do it, but it would take a long time for a human to do it. So a lot of what they'll do is rewrite things in different kind of domains to make it easier to integrate, and then go from there. So you could study computer integration systems and stuff like that and figure it out, but I wouldn't lose sleep over it. Anyways, I know the way they want you to do it is basically a u sub on this thing. So u is 1 plus square root x, and it's basically because I automatically see the derivative is sitting right here. Du then is the derivative of that, which should be 1 over 2 root x dx. Okay, so that's just such a common derivative that people kind of know it. Y equals square root of x is x to the 1/2. So y prime is 1/2 x to the negative 1/2, which is 1 over 2 root x. Okay? So if your job was doing calculus all day long, you would probably know the derivative of the square root of x is 1 over 2 root x. You just kind of have it memorized. So as soon as I saw this part in here, I was like, ooh, that sells it. I'm going to do my substitution on this part. In general, in my brain, my substitution program says, look for parentheses. Whatever's in the parentheses, let that be your u sub. Okay? If doing your u sub creates less symbols after your cancellation, then that's the correct u sub. Okay? So that's the computer program. That is actually how the computer integral, the first computer integral programs worked. They have counting algorithms inside the computer program, which counts the number of symbols. They'll do it some sort of u sub. So they'll have a count on the number of symbols before, and then a count on the number of symbols after. And then if it's less, then they use that u sub and integrate from there. And then they have the tables coded into the computer program, and it evaluates it based on those tables. Okay. So anyways, for us humans, it just depends on your experience. So my experience is I have the derivative in my brain encoded in my hard code, right? So I could see that as the derivative straight off. So I know this is my u sub, and I get my dx value is 2 square root x du, and then I could do my substitutions. So this would be the integral, and I'm going to go ahead and change the limits as well. So for 9, u of 9 is going to be 1 plus 3 is 4. U of 1 is going to be 1 plus 1, which is 2. So I'm going from 2 to 4. And then I have 1 all over square root of x times u squared. And my du now is 1 all over, oh sorry, my dx now is 2 root x du. And then the root x's cancel, so I'll have 2 times the integral of u to the negative 2 du. Okay, sorry for going off the page. That'll be 2 to the u to the negative 1 divided by negative 1 evaluated. And then that's negative 2 all over u from 2 to the 4. And then that'll just be negative 2 fourths minus negative 1. So plus 4 fourths, which of course is just 2 fourths, which is 1/2. I have no idea how your computer did that. Just be aware. Don't use the computer for your tests and stuff like that, because I'll know, because I studied that. Yeah, that's the answer. If you have another, maybe there's some weird creative way to get a different answer, but whatever answer you should get, it should be unique. I can't imagine a different answer for this. The answer you got is not equivalent to this answer. Right? And it seems like it should be unique. I can't imagine it being two different answers, even with the family of curved things. Okay, maybe there's some weird discontinuity going on, but I have no idea what the computer did. Okay. So hopefully that answers your questions, and I'll be doing some sort of final review over the weekend and this coming next week. Test 4 is next week. If you're going on the Calc 2, and I assume you are, make sure you get these integrals down pat. It's basically like knowing your addition tables and stuff like that. It's really important. You don't want to get too crazy about it, but you got to know how to do it. So when somebody's talking about it, you're not sort of just mystified in your brain trying to think through an integral when you should be listening to what they're saying. All right. So I hope that helps. Okay.